And so for our examples, and the reason examples are here in this video rather than the previous one is that it all comes together, right? Just as we explained, why are we doing any of this is to make predictions. And so we could have showed you some examples about correlation, but we would have to do the exact same examples now because we're going to try to make a prediction in this example, and we need the correlation step that we did then to help us make a prediction. So we need to do all of that here. It all comes together in these correlation regression problems. So in this example, we're trying to predict a student's GPA based off of the hours of video games that they play each week. So again, first off, when you think about R squared, explained variation, we've already covered this, right? Why are people's GPAs different? Why is yours different from the next person? How many video games you play would be one piece of that pie. Would it be all the pie? No. Would it be none of the pie? Absolutely not. This matters at least a little bit. And so find and interpret the linear correlation coefficient. Notice that we're going to have to take that value of R squared, which is 0.172. We're going to have to square root it. But notice that if you are given R squared and you square root it, mathematically you're going to get a positive number. That will be the absolute value of R, but then you have to determine if R should be positive or negative. Remember, R squared cannot be negative because R squared is squaring a value. Anytime you square a value, it has to be positive. So R squared has to be positive, but you might have to look at the problem and say, should R be positive or negative? Well, how would I know? Remember, we said that the sign of the slope and the sign of R will align. And so in this case, notice my slope is a negative 0.1, and so I have to attach the negative there myself. If I were to put R equals 0.415, that would be not completely correct. And once we have that, we can write out our interpretation. I'm going to start off with the context of the problem for full-time college students. And I'm going to say what sort of correlation we have. Again, there are three parts. We have to assess the sign, positive or negative. We have to say, because we're dealing with R, it's a linear correlation. And then using my guidelines, the value of 0.415 would fall into the weak category. Again, if you wanted to say moderately weak or use some more, slightly different cutoffs or terminology, that's fine, as long as you're in the right ballpark. The biggest thing is you wouldn't say none and you wouldn't say strong in this regard. And what's the correlation between the number of hours video games played each week and that student's GPA? Then we get to coefficient of determination. Again, as we talked about, we can write it as a decimal as it's done in the problem. We can go ahead and convert to a percent. And as we said, the R squared tells us what percent of the response variable is explained by this relationship we found. So again, thinking about that pie chart, we would say that part of your GPA is this reason, part of your GPA is that reason, but how much? And so this tells us that 17% of why a student has the GPA of what they do can be explained by this relationship that we found between GPA and video games. That video games make up 17% of why your GPA is what it is. So if you're playing too many video games, that's going to bring your GPA down a little bit. If you're not playing very many video games, it might bring your GPA up a little bit. Not the entire factor. There's so many other factors involved. In fact, if you think about a pie chart, there's 100% of the area there. It means there's 83% as other things, right? Sleep and nutrition and background and major and age and who knows what all else explains why your GPA is what it is. This is just one small piece of that puzzle, and specifically 17% of it would be because of video games. Interpret the slope, and again, we're going to talk about making sure we use these words on average and expected. Again, use one or the other when you're interpreting these. The slope is negative 0.1, which means every time we play one more hour of video games, our GPA goes down 0.1. For the y-intercept, we have to first say, is x equals 0 reasonable? And in this case, you would say, is it reasonable that a student plays no hours of video games in a week? You say that's absolutely reasonable. Maybe that applies to you. Maybe it doesn't apply to you, but you probably have a friend who that applies to. So it's absolutely reasonable to say that x could be 0, and so I am free to interpret the y-intercept. And so what that means is if I play no video games, my GPA is expected to be at a 3.4. Again, that's why we're using the word on average or expected. There are tons of people who don't play video games and their GPA is not 3.4. This is not to say that this is the end all be all. I can make this exact prediction of I know that when a student plays no video games every week, the GPA of that person is 3.4. It's saying that's the average, that on average, all of those students who play no video games a week tend to be about a 3.4. Some will be higher, some will be lower, but that tends to be the case. That's my best prediction for what happens when I know a student plays no hours of video games. And then specifically, we can predict the GPA of a student who plays 8 hours of video games a week. And this is, as we mentioned, this would be when you would just plug into the equation. However, if we go back to our guidelines, should we use the prediction equation because our correlation is so weak? Right? Our correlation is negative 0.415. Is that good enough to use the prediction equation? This is definitely a tweener case. These are the types of areas that you might want to look at a picture. We don't have a picture to kind of embolden your case whether you should or shouldn't use it. So this is not a situation where there's a black and white answer. I just want you to be thinking. I want you to be thinking this might not be an appropriate use of the prediction equation. Okay, so just again, be on your toes, be thinking about this. The biggest thing that you need to be aware of as you move forward into an exam on this material is if you're thinking, maybe I should, maybe I shouldn't, your brain's in the right spot and you're going to do well on this type of question exam. If you're not thinking about that and you're just blindly saying, yep, we always use it, don't think about it, that's not where your head needs to be, right? So be thinking, should we use it? Should we not? This is a tough case. And again, just to work out the problem in case we do, so for those situations, you're kind of prepped for when we do want to, we would plug in that 8 into X, and that would give us 2.6. So we can say that Y hat is 2.6. Again, remember, Y hat's the predicted value of Y. We would predict that a student who plays 8 hours of video games a week would have a 2.6 GPA. And again, that's just a prediction. That's just on average. We're saying the students who play a decent amount of video games every week, they tend to have GPAs in the 2.6 range. Does that mean all of them do? No. It just means that when you're playing more video games, it's taking away from study time, homework time, things like that. It means your GPA is probably going to be a little bit lower than if you spent that time on your schoolwork. And the last question here, student who plays video games 7 hours a week has a GPA of 2.8. So what is the residual? And again, now I need to find Y hat. I need to know what the predicted value would be. So I do the same example. I would predict that student has a 2.7 GPA. So if I have a GPA of 2.8 and I'm predicting 2.7, and it's kind of off the bottom of the screen there, but we're just going to subtract Y from Y hat, and that would give us a residual of 0.1, as in the difference between Y and Y hat. That is what the residual is. Last example here, a school cafeteria is a salad bar. It's priced based on weight. Salads cost 25 cents per ounce. Student fills a container that weighs 10 ounces empty. So that means the container has a weight of 10 ounces with you put nothing in it. Denote X to be the weight of the filled container and Y to be the price the student is charged. And we end up with this regression equation and the sample linear correlation coefficient given as such. So find and interpret R. Notice that I just translated simple linear correlation coefficient, that is R, so I just found that, reported it, and then I can write out this is a very strong positive linear correlation, or you could say almost perfect, right? Because 1 or -1 would be a perfect linear correlation. So this is almost perfect, not quite there. You would assume it's almost perfect and not exactly perfect because of rounding and ways that scales work. You can think of that if you want. If you don't want to think about that, you don't have to at all. Calculate R squared, so I'm going to take that value, I'm going to square it to get R squared. That gives me 98%. Interpret in the context, again, how much of Y is because of what we've done with this equation. So we could say 98% of why you're paying what you're paying for a salad is because how much the salad weighs, which makes sense. And again, in reality, you'd say it should be 100%, right? But you say there might be, again, a little error in scale or something like that. So it may not be you're paying what you pay for the salad explicitly just because of the weight, but you'd say there's a little bit of variability from scales and things like that. But you're basically the reason why Again, that's explained information, the reason why. The reason why you're paying what you pay for the salad is how much salad did you get? That should make sense to you, hopefully, just from a common sense standpoint if we get out of math brain here. Explain in words what it would mean if x equals 10. Well, if x equals 10, that means that we don't have any salad, right? Because x is the weight of the container with the salad in it, but the container weighs 10 ounces when it's empty. But if you plug 10 into the equation, you get -2 plus 2.5, which means y hat equals 0.5, which means if you walk through there with an empty salad, you have to pay 50 cents for the container. Right, so these are the types of things I want you to be able to think through on this scenario, right? You see that the container weighs 10 ounces, so if x equals 10, that means you didn't put any salad in it. And how much did you pay? Well, you plug that into the y hat equation, you plug 10 in there, and you get 0.5, which means that they're charging you 50 cents for a container, which is not uncommon for places to sometimes charge for containers. Interpret the slope. Slope is 0.25. What that means is that every time you increase x by 1, that's what happens to y. So in this case, every time x, which is the ounces of salad that you have, every time you add an ounce of salad, you have to pay 25 cents more. And notice again, I'm using the word expected because r is not 1. If r is 1, I don't have to say expected, but r is not 1, so I need to have that word expected or on average. Appropriate interpret the y-intercept. Is it appropriate to interpret the y-intercept? Can x equal 0? And this is the counter idea from what we had in the last example. This is where we don't want to interpret the y-intercept. Why is that? Because if the container weighs 10 ounces and x is the weight of the container with the salad, that means that you have -10 ounces of salad. That doesn't even make sense, right? So it's not even remotely possible for x to equal 0. So this is the situation where you always want to ask yourself, when interpreting the y-intercept, is x equals 0 reasonable or possible? If you're not asking yourself that question, you're 50-50 on this, because about half the time you're going to have to interpret and half the time you're not. Okay, so I want you to think to yourself, is it reasonable for x to equal 0? In this case, x is the weight of the container plus salad. The container weighs 10 ounces, so x cannot equal 0. So I'm not going to interpret it. The y-intercept exists. The y-intercept is -2. Don't get me wrong. It does exist. It is a number, -2. But it doesn't have an interpretation. It doesn't have a meaning. We can't talk about it as a thing. It's just a number that has no meaning. And that's what we say here. When we don't interpret it, we're saying there's just no meaning to it. This has meaning, the slope, because we're saying every time you put another ounce of salad in, you have to pay another quarter. That's meaningful. That's helpful. If I say, I've got this salad. Oh, I want a little bit more, I want some more croutons. I want some more lettuce. I want some more whatever, right? That means every time you add another ounce, boom, there's another quarter. You know what you're going to pay. It has meaning. The y-intercept of -2 does not have a meaning. It is no tangible thing we can talk about because it's not possible for x equals 0. And the last one, how much is a 12-ounce salad, not including the container, weigh? So if I don't include the container weight, how much does a 12-ounce salad cost? I have to add the container weight in before I plug in right. X represents the weight of the salad and the container. And so I can't just plug in 12 to the regression equation because I have 12 ounces of salad plus I have 10 ounces of the container, so I have to plug in 22, and that leads me to a predicted value, a y hat, of 350.